afternoon, everybody. Welcome to this installment of our Earth Talks. Today we have the pleasure of hosting Professor Sama Pisupati, who will be talking to us about his presentation on securing domestic critical mineral supply chains, looking at Penn State efforts from lab to pilot scale. So I don't believe he needs any introduction, but since I have that in front of me, humor me, I will tell you about Professor Pisupati. Dr. Sama Pisupati is a professor of energy and mineral engineering and chemical engineering here at Penn State. He is the inaugural director of the Center for Critical Minerals Research, which was founded to promote sustainable recovery, sustainable resource recovery, and circular economy technologies. Sama established and led the first ABET-accredited undergraduate program in energy engineering in the US, where he also served as a program chair for 11 years. His academic leadership includes roles as the director of online education in the EME department and the co-director of coal science, of the Coal Science and Technology program in the EMS Energy Institute. What he's here about today, his interdisciplinary research focuses on combustion science, geothermal energy with carbon dioxide sequestration and extracting critical and rare earth elements from unconventional resources such as electronic waste and acid mine drainage. He has served as a principal investigator on and co-principal investigator on 75 externally funded projects, and he's managed over $10 million worth in research funding. He has authored more than 240 research publications, one of which has resulted in a US patent with 3 additional patents pending. Professor Pisupati is a fellow of the American Chemical Society and the Indian Institute of Chemical Engineers. He has held numerous leadership positions in national and international professional societies, including organizing over 30 major scientific symposia and serving as an associate director, associate editor and conference chair for key journals and events. His work has received widespread recognition, including the R.A. Mishalka Medal for Innovation and Science Leadership, as well as receiving the Best Paper Awards, and as well as receiving several Best Paper Awards. He is this year's recipient of the Wilson Award for Outstanding Service to the College of Earth and Mineral Sciences. Without further ado, we welcome you, Sama, and look forward to hearing what you have to say. And we welcome the audience online as well. Thank you.
Thank you very much for joining this afternoon at 4 o'clock. You could have been doing other things, wonderful things, but I appreciate. And this Earth Talks series, actually, and particularly with respect to critical minerals, when Dave Russ, who is very, very dear and very supportive of our activities here. He serves on our Geosciences Alumni Board, and he asked me if I could share what we do here. And I thank him because he has been supporting us since 2019. I very well remember Dave facilitated our meeting with the Office of Science and Technology Policy when Steve Fortier was the chair of the commission there, and we went to West Wing to promote our case there. So thank you, David, and others also, several of them. Ned set a benchmark last time, and I hope I can meet that standard today. And what we are going to be looking at today, or what I intend to share with you all, is basically what we are doing. I mean, you all know right now, how important these critical minerals are. And last week, Ned had made an excellent case about the importance of these things. So what we are doing and where our story started here. Again, what we have here is there are several faculty members I can think of, and this morning we were counting and counting and counting. There are at least 100 faculty members on this Penn State campus directly or indirectly related to this kind of research, critical minerals research, actually, one way or the other. So to bring everybody together, we formed this center, and we try to establish nationally recognized programs here. So I will share with you some of those experiences. So first of all, what drives this is the sustainable energy profile, basically, what we want to accomplish. Whether we are not is again a big question, and I'm here for debating on that for hours, actually. And if we want to, a role of critical minerals in that particular new profile, energy profile that we are looking at, and why we are concentrating here, at least on secondary resources, because primary resources like basanite, monazite, and things like that, we don't have them here nearby, and we do have a lot of secondary resources here in Pennsylvania and in this region. So we will be concentrating, and I'll make a case for it. And challenges in critical minerals. A lot of times we face these questions, like whether it is possible, whether it is economically viable, whether it is whether we can commercialize these things, et cetera, et cetera. We'll see what challenges are and what are the innovations that we basically have come up with, and we have taken from lab scale research and publications and things to pilot scale, and we are ready to go to the field, actually. So that is what I will share with you, some of our experiences, and then next steps, and then we can discuss together. Okay, so that will be my outline. So for net zero emissions, that is what is driving all of us for critical minerals. Net zero emissions, the way it is projected, whether we accomplish this in the timeline that we are thinking about or not, that's, as I said, it's a different question, and that would be a topic for a different debate. But what we learn from this is the fossil fuels are expected to decline. Use of it is going to decline. But I'm a firm believer that they will never go away from our energy mix, and they cannot. There will be some fossil fuel energy, for energy applications, and electricity use is going to go up. Obviously, that is the projection, and there is no question about it. That electricity has to come from solar energy, wind energy, or renewable energy, so to speak, or it has to come from nuclear is another possibility. Okay, nuclear, micronuclear, and things like that. But when we generate electricity for even hydrogen, people are talking about hydrogen economy. For hydrogen generation also, we need a lot of electricity, and that electricity has to come from, again, one way or the other, from renewable energy sources. Renewable energy sources, we need to have some kind of storage system. So that is what it is. Electricity is the dominant fuel, particularly when we go to the transportation sector, when it goes into EV vehicles and so on. We need a lot more, actually, electricity. So that's what is the message here that is driving us. So okay, the key for zero emissions, I always say this, it is energy storage, either grid scale energy storage, or if we want to go particularly industrial sector, which are very high temperature oriented industries like iron, steel, melting, paper, and things like that. If they have to go, they have to use more and more either electrification or hydrogen. Hydrogen, again, it comes back to electrolysis. It comes back to a lot of these things to produce that, hydrogen. So electrification and hydrogen, again, it goes back to solar, wind, micronuclear reactors, and we need storage for transportation. There is no question about it, anything. And the third thing that I say is, even if we want to go for transportation, we have already met in power sector. Right now, we're lagging way behind with respect to huge storage systems for power generation. So energy storage, energy storage, energy storage. Those are the key words that will drive, if we want to go for net zero emissions, that is what will drive us. So if we look at the battery systems, actually, most of the battery is made up of graphite, 60-70% of it, and then the key elements that we use, copper, cobalt, manganese, lithium, nickel, all these are critical minerals. because without which we cannot build one of these. And I don't want to elaborate on this. One point that I want to mention is that if we look at net import reliance of these critical minerals that we're talking about here, and it is not rosy picture that we are seeing here. I mean, we have talked about this last week also. Ned has made a case about this one. Net import reliance for these critical minerals is very high. This does not include rare earth elements. Actually, this is battery materials that we're talking about. One point I want to mention is that you can see the countries that we heavily depend on. And the second thing that I want to mention is global production. If we look at how much we are producing, 130 million metric tons, 26 million metric tons of lithium here, and so on. If we look at this lithium, entire lithium, and 8.3 million tons of cobalt, if we don't send to any other industry, just sending them to only battery making, we can make right now 26 million vehicles. And cobalt about in the same range. Forget about 21, 22, 23, 24. We don't have to debate, but that is the range. You know how many million vehicles we would be needing by 2050? If we want to go for net zero and convert all entire transportation, 2,000 million. Not 20, 2,000 million or 2 billion vehicles worldwide. Where is the lithium? Where is the cobalt? Where is all these minerals? Oh yeah, we're not going to be using cobalt, we're going to be using sodium. Nothing will materialize in the next 10, 15 years as quickly. I mean, we have seen hybrids, we have seen everything. Market penetration will take time. So the challenge for us now is to get those minerals, and how to get those things is the challenge. The challenge starts with the resources. We have to explore these. First of all, high assay materials. If we have the resources in the ground, unfortunately, we don't have much in the East Coast here. Most of it is in the West, but it doesn't matter. It's still the United States. That's fine. So that is first step. The second step is mining and reclaiming. We have actually looked at some of the resources where we find a resource in the core, but it is only 4 inches, 3 inches, 5 inches, 20 inches, whatever it is. How do we get that? That's a challenge for mining engineers. Okay, even if we get that, we have to crush it, grind it, and pre-concentrate it. We don't want to process millions and millions of tons with acid to get these critical minerals out. So if we were to do that, that is crushing, grinding, and so on, it is basically pre-concentrating. And then once we get that involves mineral processing, okay? And we get the concentrates out of it, and then let's say we concentrate it to 20%, 30%. That is really optimistic that I'm talking about. And then that has to be treated with acids, bases, whatever it is, chemical methods to extract those things. Once we extract those things, again, those are oxides, hydroxides, the form in which they come out. That is not the form most of the time we use, and we get all 15 rare earth elements together and all these transition elements together or something like that, depending on the process we use. That is not going to work. And what we have to do is we have to reduce them to metals to make the alloys, to make whatever we need. So the next step is metal processing, basically metallothermic reduction, or one way of reducing them to metals. Metals, then we can combine them and make alloys, and we can make permanent magnets or super alloys or whatever type of alloys that we need for high temperature applications. And again, advanced manufacturing will include novel batteries and things like that for our transportation industry, as we talked about. And all these things we have to do in an economically viable way. Who is our opponent here that we are facing? Who are we up against? China. With a stroke of a pen, they can slash the prices. They can say, ABC company, as Ned was saying, you will not supply this elsewhere, or no other country. Done deal. No opposition. Here, that is not the case. Economics, I mean, I've had the privilege of visiting China several times when I was working with gasification industry and so on and so forth. They always say this, oh, we are very competitive in making this synthetic gas or this or that. Okay, great. What is your price of coal here? They go, well, coal is allocated by the government. Okay, so feedstock price is not included in your economics. What about the land here? How much land you need to build this plant, and what is the... No, actually, nobody owns land in China. Nobody owns. Even a homeowner does not own the land, leases the land from government. So land price is not included in the economics. So their economics are not, I'm saying they're not apples to apples to compare. So it's different economics there. Okay, I'm not saying good, bad, ugly, but that is the economics that we are trying to compete against. And if we extract one element or two elements or three elements, we may not be in the business. We have to find ways to extract as many as possible. And economics is something that I can talk for hours, actually. It may not be economical sometimes for certain things, but we have to do for national security. I give this example all the time. You probably have heard somewhere this one. When a child is born to a young couple, will they do any economic analysis on buying diapers? Oh yeah, Huggies versus this or that's economic. But why should I spend $5,000 until 5 years to get these diapers for this child, whether the child is going to become a scientist or an artist? Is that child going to repay me? Will any of us do that analysis? It is required. We do it. That is what we should do, and then only economics. Of course, still, obviously, companies require economic analysis. And you can see this picture, it involves a bunch of disciplines where geosciences, mining, mineral processing, hydrometallurgy, pyrometallurgy, material science and engineering, chemical engineering. And finally, we need also business and finance, energy business and finance right here. All of these, most of these disciplines are in our college. That's the beauty. And we have nationally ranked academic programs. Intelligence is here. And we have Center for Critical Minerals to bring all the faculty together. Materials Research Institute, worldwide, very well-known materials folks are here. And Battery Research Center here, right here. So who else can compete with us in taking the concept to commercialization? Of course, Penn State never commercializes, as I always say. We don't build plants. We're not authorized. That's not our game. What we play is we develop new knowledge and we train workforce. But that knowledge will be transferred to the industrial folks, and they are the people who make it happen. So we need to collaborate with industrial partners to make that happen. All right. So what are the environmental challenges in getting these things out from these ores that we are talking about? 1 ton of REEs to produce, we need 2 tons of water. Yeah, not a big deal. 1.17 hydrochloric acid tons, 1.64 tons of sodium hydroxide, 11 tons of sodium chloride, 59 tons of raw ore we have to process to get 1 ton, and then approximately 4 tons of sulfuric acid. So this is the environmental consequence of it. So it has rare earth elements and critical elements production is not like clean, green, and wonderful operation. Am I talking English? Are you guys following? I ask the students all the time. Okay. So how much do we have these resources actually? If we look at, the United States has 1% of the world's resources. Again, as Ned was mentioning, these are what we know of. There may be other things that we did not even look at actually, but China has 37%, Vietnam has 18%, Brazil has 18%, and so on. Most of these are in the West Coast. Nevada, California, in these ores that we're talking about. And one thing that we need to keep in mind is we need to go for secondary resources, which is basically as a result of our past activities, not just coal mining, any copper mining, zinc mining, all those activities. We have taken the best and we have dumped in 20s, 30s, 40s the worst material, thinking that we will never use it. I don't know if you guys know Edward Steidl, who was our dean, right? Some of you may not know. In 1950, he predicted that by year 2000, the ash that we are throwing out from power plants and all the waste that we are dumping today will become a precious commodity. For what? He specifically said in that bulletin, for rare earth element extraction. Visionary. All right? In 1950. Yeah, just we're 70 years late. So, number of years it takes to obtain a permit. Australia, Canada takes 2 years. United States takes anywhere between 7 to 10 years. That's not in my hands or your hands. That's the way our process works. And these are the secondary resources that we can go for. And these, again, there are different permits that we need, but these are the sources that we can get hands on and clean up the environment. We have to do it. We want clean air, clean water, clean land. So we must do this. Every ton of iron, ton of aluminum that we produces almost 1.5 to 2 tons, depending on where we are, depending on how we use, tons of red mud. All 200 years worth of coal mining activities before 1977, SMECRA, there were no laws actually in how they should to reclaim and leave the land. So people just walked. That was the law. I mean, they did not violate anything. And all those mines are spewing out acid mine drainage. And electronic waste, every year we change our models, so we need to keep this in mind, and this is what all these resources are there, and we should go after them. And we concentrate here acid mine drainage. We thought that this is the lowest hanging fruit for us, and we are concentrating on this. We started our research. Let me tell you one thing. What I'm presenting here today, I want to emphasize, this is not just my research here. I don't do anything according to my administrators. I just get paid at the university. There are several of my colleagues, several of my my scholars, students, all of us in Center for Critical Minerals and elsewhere on campus have worked together to get this one. I just want to acknowledge everyone here. Acid mine drainage, this is the state of Pennsylvania and how many sites, how many abandoned coal mines are there. And these are the resources and that we have. Not all of them are gold mines. Let me put it this way, not REE mines. But we need to extract these things. So if we clean up this environment and get some of these minerals, we are remining, remediating, we are reclaiming some of these things and reducing national dependency or net import reliance for these things. And what typically people do is, acid mine drainage water comes out at a pH of 2, 2.5, 3, 3.5, whatever it is, depending on the source. They treat it to bring it to 7 pH because water has to be treated. Otherwise, that water cannot go into streams and lakes and rivers and things like that. So that was their goal. So taxpayer is paying for it to treat it, to get it to pH of 7, and water meets the regulations and they leave it, they discharge it into streams. Whereas the solids, which were in dissolved state, will precipitate during this process. They all settle down to the bottom of the lake or pond, so to speak. And once in 2 weeks, 3 weeks, 5 weeks, 2 months, the sludge is pumped to a next door pond. This is the pond, this is the sludge, which is basically the precipitates that have come out. It has calcium, it has sodium, it has neodymium, it has praseodymium, it has cobalt, it has everything that can come out at a pH of 7. These have been sitting there for decades. Nobody touched them. And if we can go that, that's a rocket fuel for rare earth element industries. Okay? So first of all, we can clean up our water, clean up our lakes and streams. And this is not just Pennsylvania problem. I'm just putting up here. This is wherever we had coal mining in this region, that's where it is. So I explained to you the process. You take the acid mine drainage, you adjust the pH, and everything settles down to the bottom. You take the sludge and pump it into next door. And this is actually, you can see, this is my colleague, Mark Klima. And I was there. I mean, you can see the bald head, right, clearly. So we were getting that sludge from there, to work on this. So let me put the background here in context. We have developed a patent-pending 3-stage process for taking out iron, aluminum, rare earth elements, cobalt, manganese from these things, whatever are there. Let me go to the fundamentals and the basics on how it is generated. So we have developed those innovative methods here, and we have studied actually which ligands work. In the field, typically they use sodium hydroxide, calcium hydroxide, or lime, or whatever it is, an alkaline material to neutralize the pH. Sodium hydroxide, is that the best? Not really. So we have looked at various ligands. All these ligands we have tested in the laboratory and produced, the precipitation, studied the precipitation patterns actually. And then what we can see here is, actually, I mean, this is a busy slide. All you see on the y-axis is basically the cumulative recovery, and on the x-axis of each of these graphs is the pH. Now you can see. And here the sodium hydroxide at a pH of 7, when we bring it, not all of it is coming out. We need to go to a pH of 8. But regulations require for us to go to about 7, and then we can get whatever we can get that meets the regulations. Water goes out. Water goes out, right? But we are not getting all of it. And I'll show you actually, we don't get cobalt out of it, manganese out of it. Manganese regulations are coming even for drinking water now in Pennsylvania. And we need to go to pH of 9 or so to get those things. So they are not recovered here. They didn't care about these minerals. I'm not blaming them. That's the requirement. Okay? And then we came up with, while studying this, we came up with sodium carbonate. I want to highlight this sodium carbonate at a pH of 7 can bring everything out. Very little can come out at a pH of 8. That is, and sodium carbonate is much more environmentally friendly compared to sodium hydroxide or calcium hydroxide. So that is one thing that we have come up with. So it's less hazardous, so environmentally friendlier. And also at a pH of, as a function of pH, if we look at with sodium carbonate here, at a pH of 4.55, if you go to 5, aluminum is coming out. Rare earth elements are not coming out at a pH of, it's not rocket science, folks. So what we can do is we can devise a 2-stage operation here. One stage at a pH of 5, aluminum can be precipitated and add more sodium carbonate, and then go to a pH of 6, 7. We can get, if we go to 7, we can get all REEs out. Staged precipitation. Okay, staged precipitation. And 2 stages. Staging allows separation with the same amount of chemicals, so to speak, roughly, right? Selective precipitation by CO2 mineralization. Another innovation that we've figured out is that in these experiments, when we put, because we are using carbonate, we thought, why not pump CO2 into it? By using CO2 actually in here, you can see what we understood is that at a pH of, as a function of pH, tree recovery, if we look at tree recovery grade also improves here. Yeah, let's go to this graph. This will clearly show. With carbonate, without carbonate, actually, or with CO2, without CO2, there is a 15 to 20% jump in the recovery. Okay, don't ask me how much CO2 can we sequester with this one or utilize with this one. It's not much, but whatever it is. All right. And so step 1, aluminum. Step 2 is REEs. We can separate them. And then I'll show you here cobalt and manganese. These are 4-way diagrams, which are basically, which tell us, oxidation state versus pH, which state these things are. At a pH of 7, if you look at Mn is dissolved. This is not the state. So we are bringing from 2, 2.5, 3 to the right side, and it is still dissolved. Mn and cobalt also at a pH of 7, it is still, until we go cross 8, it won't come out as cobalt hydroxide. So most of these sludge ponds, some of it has come out, but most of it did not come out. So it is still there in the water going. So these are the battery materials we're after: cobalt, manganese, nickel, zinc, nickel, and these metals. Okay? So what we have done is, instead of going this way, if we push it this way, our operation, what will happen? If we can oxidize these things, they will come out as manganese oxide here and cobalt hydroxide here if we push it at a pH of 7. If we do this at 7, we don't have to take it to 8 or 9 by adding more and more base, and we cannot discharge that water at a pH of 9. So we have to bring it back by adding more acid. We are avoiding those 2 steps. That is the innovation here. And by oxidizing it at a pH of 7, we're able to get cobalt manganese out. That is the principle. It's nothing, no major thing. So we are, instead of pushing to the right, adjusting the pH, which was the logic that we used for other things, now here the logic is oxidizing it. So what oxidizing agents we can use by separating it at 7 avoids additional acids. So this is what the greener aspect of it. Okay? And then what we do is, in this one, we used several oxidants we have tested, permanganate and ozone. Ozone seems to work really well, good recoveries and so on. So we have studied kinetics and things like that, all these things, at what rate they will precipitate and at what rate the growth of the particles, the precipitates, and then again dissolution after a certain rate, right, ripening and dissolution and other things, fundamentals. And then what we did was we said, okay, we can use this and build a pilot scale unit. We were confident. The mineral grades that we are looking at are not super attractive at this stage. Again, this is the result that we published a few years ago. Now we are getting really high grades actually by purification. I'll share with you. So basically 3-stage process. Cobalt and manganese can be recovered, and oxidizing agents. Ozone is the best oxidizing agent that we can use probably. And this is a chemicalless process. We are not using any other chemicals in here. And so we are able to recover 95% of cobalt, manganese, 95% of rare earth elements, and aluminum 85%. Iron as a pre-concentration, we take out iron, because if they spill over aluminum to the rare earths, that will lower the grade. We have to purify it because those are very small quantities. Okay, so now this is the schematic that we came up with, and we have tested the purification again. The grades were not, obviously, in the first pass. Sodium carbonate was not very high at pH 7. Grade was 1.4. So we redissolved again at a pH of 2, and again precipitated again the same process. Iron out, aluminum out at a pH of 5. 2 cycles, after 2 cycles, we're able to get 90% purity of rare earths. Similarly, we have a purification cycle for aluminum, and we were able to get 90% pure aluminum there. Okay, cobalt and manganese, it is a much more detailed study, and we were able to do that too. Actually, this is a little bit now dated for us. Now we have even much better results. We can even separate them: 90% cobalt, 90% manganese, 90% nickel, 90% purity by zinc, etc., etc. Our research scholars have done an excellent job, actually. Graduate students have worked so hard to get this one. Not me. All right. So we have tested this at a 20-liter scale, lab scale, and then we have built a continuous unit which processes about a barrel of a day, something like that, in that neighborhood. And we went to the Congress and we got a $2 million grant to build a pilot scale unit. So we went and built a pilot scale unit, actually, which processes 10,000 gallons per day equivalent. So per minute, it comes out to be 7 gallons per minute. To give you an idea, a full scale, most of the acid mine drainage flow rates are around 300 to 400 gallons per minute. We are building something for 7 gallons because we are transporting acid mine drainage from the site to campus. We don't want to put a pipeline here, or just to show the process. And this is big enough process, actually, to do that. And we have operated this one, shaken down, operated in the sense shakedown operations are complete. And this is the acid mine drainage site that we go to and bring it with a truck, 2,000-gallon truck, and we operate this. This is the facility, and I'll share with you in a minute. And we can extract aluminum, rare earths, cobalt, manganese, nickel, zinc out of it, 90% pure metals. So this, again, I want to explain you, the title of my talk was Lab to Pilot Scale. It is very easy to find something in laboratory and patent it, or and say, yeah, we have a process, we did research, we know how to do it. But building a plant out there and doing this operation at the scale is not easy. Is not easy. And first hurdle it was, actually, this was a cold water slurry building that I was, again, in my past life, when we were doing cold water slurry research here in the 90s, turning coal into oil substitute as cold water slurry. If you guys remember, Department of Energy and Department of Defense were big when the oil embargo was there. So we used this building, and we thought, okay, yeah, we have the mezzanine, we have these 1,000-gallon tanks, and we can easily convert this into that. And then we went to OPP and said, we want to do this. OPP said, no, we have to do a structural analysis of this. And they came back and they said, what you are proposing, these structures will not take it, and these tanks will not take it. We need to gut everything out. And then, this is the state. The lighting was not great. Anyway, this was used 25, 30 years ago. So this is the building. This is on the East Campus power plant, if you guys know, on the whatever Porter Road, and by the side of our Medlar Field next to that. This is the building. And we hired an engineer, and engineering firm, and completed these things. And then we installed a 4,000-gallon tank where the acid mine drainage will be actually transported by trucks or tankers. And then these are, again, as the parts were coming in, these are the pictures. And this is kind of established. We were almost 8 months late into the project, but this is all kind of completed. This is on June 10th. We have taken this picture. And shakedown activities, you can see this is the site where the acid mine water is coming, and the tanker is coming and filling this 4,000-gallon tank. And I'll show you here, just for fun, some of these things. When the tanker comes and fills, and it basically mixes the water, and yeah. So, and we store the water here. And this is, again, these are, as I said, our process. We take the water, which is at 3.5 pH, whatever it comes, and we adjust the pH to 4. All iron comes out, precipitates out at that time. Filter it. Iron is an impurity, so we take out that iron and take the filtrate to a next level tank, and that tank will be aluminum tank. We add same sodium carbonate here, and this is the iron tank that we were testing actually during shakedown. And you can see this is where these two basically bubble, these caps actually bubble air into it and then oxidize the water to take out the iron. And we want propagation and the recirculation pump that is running and recycling the water. So to make sure that iron gets oxidized here. And this is a sodium carbonate feed tank. Only one sodium carbonate feed will be there, and it is controlled to different tanks to maintain the pH at different levels, stage precipitation. And these are the pumps that control the flow rate of sodium carbonate based on a pH measurement, which is, again, this is the controller that controls the flow rate to different tanks: iron tank at pH 4, aluminum tank at pH 5, and rare earth elements at pH 7. And again, at same pH 7, we precipitate. What else? Cobalt, manganese, nickel also. We don't go higher, right? Cobalt, manganese, nickel. And what happens is when you oxidize those things, pH drops. So we need to add more sodium carbonate just to keep it at 7. So for all the applications, we use the same thing here. I don't want to waste time in showing these videos, but this is the aluminum precipitate that we got. Okay, again, this is not the best precipitate. During shakedown, we got that with a little bit of iron spillover. We didn't do that. And this is the oxidation. This is basically the ozone system. Pinnacle Systems, who is our partner, supplied this ozone generator. And this ozone is pumped into the second tank. And then we monitor actually the pH and inject some sodium carbonate to adjust the pH if required. And this is where we oxidize every transition element to its full oxidation state. And then all that will go to the last tank, which is the settling tank, where the particles will try to settle down. And if they don't settle, if the residence time is not enough, we take this one, and then actually there are a bunch of tanks that you have seen with Fe, with Al in the diagram. I'll show you that. And that's where we actually make these particles settle. Okay, and then the overflow is what goes into our fill. This is actually the iron. This is the cobalt, manganese, nickel precipitate that we got from. Again, we didn't do full scale operation for hours. This is just one day when we were shaking up. Again, we had 4 or 5 graduate students and 6 undergraduate students, 2 postdoctoral scholars, and 2 full-time staff members working on this one actually over the summer. And we collected the rare earth element precipitates also here. And one message clearly is that, yes, what we tested in the laboratory scale, we confirmed in our pilot scale unit. We were able to recover 94%. The chemistry, process chemistry was validated. 94% cobalt recovery, 81% nickel recovery, 94% manganese recovery, and you can see rare earth elements. So yes, the process that we developed worked, and there are engineering problems. I'm not trying to pose a rosy picture here. Engineering problems are there in terms of filtration equipment, the obtaining required flow rates, the pump things. So we are going through those teething troubles, and we need to sort out some of those things. The game is not over yet. We're still in third quarter. We're still leading though. So it's good. That's comfort. That's so purification circuit was designed. Again, what comes out from this concentration cycle is not high purity thing. You have to put it through 2 cycles of purification to get 90%. So purification circuitry also has been designed, and we tested those things in a single operation. And we got the aluminum cake here, and we got here zinc manganese things. Again, what you are seeing here is these precipitation stages here, stage 1, stage 2, and again here we have aluminum also, This is the aluminum purifications. And again, I mentioned this to you. We use CO2 to do that. And also, again, it is a very simple process that we use, and we have built the facility here. And purification obviously will be smaller because we are getting concentrates from that, and we are operating. They're not like huge 10,000. So we have obtained the residue as well as purified aluminum here. And rare earths purification, again, you can see here after separation of iron and aluminum, rare earths, this is the concentrate that we got, cobalt manganese concentrate, and then it goes through the purification circuit again, dissolution, again iron precipitation, getting rid of leftover aluminum there, and in this one, and then finally we get the final precipitates. And we have all those samples, and we are really analyzing some of those things for the grade that we got. So in essence, we have tested the products in concentration circuit. We basically validated the process chemistry and also the process that we developed, and it shows that the AMD can be used or transformed from waste stream into a source of valuable critical minerals. Okay, we're doing some techno-economic analysis and other things also with the University of Nevada, who are our partners. I'm not going to go into those details, but I just want to give you a highlight. Okay, what next? Right? That's the question that the administration always asks. What next? Right? So now let me show you what next. So we have these concentrates from this plant, from what we do at Penn State, and we have developed we have formulated an alliance here actually with several industries which have already developed, which already have some technology that they don't know from acid mine drainage how to get these things. But if we give them the mixed rare earth oxides or mixed critical minerals, what they can do is they can take those things and separate. So we are taking, Penn State will be taking acid mine drainage and separating into all these streams, mixed rare earth oxides and things like that. And then what we do is we discharge the clean water at a pH 7, and then this will be supplied to Aquametals, who are an industry. They know how to separate cobalt oxide, whatever we are giving them, into cobalt, manganese, nickel, individual elements of 99.99 purity. And then we send this to Rare Earth Salts, which is another company in Nebraska, and they separate 15 rare earths into different pots so that samarium from here can be mixed with this Aquametals cobalt and make samarium cobalt magnets, final magnets. So as I said, oxides are not the ultimate thing. People have to use only metals. So University of Virginia has developed a method to reduce that at a lower temperatures, metallothermic reactions to chemistry to reduce them and to metals. And those metals, 99.99% purity metals, will be combined to make alloys by GE. You guys know GE, right? Okay, microwave ovens, right? GE takes our products and makes master alloys, super alloys, and then what we do is they are going to test those super alloys there for high temperature applications, as well as they perform our total techno-economic analysis. If I do it, nobody trusts. I don't know how to do it either. Don't tell anyone. So we partner with industrial partners. They are the people who do that from here to finished products, and reduction of net import reliance, and cleanup of the environment, and finished permanent magnets. Is a gram of our material going outside the country here? No. That is the goal. Right now, zero is processed in this country. If we have this process, we can demonstrate that we have 100% domestic supply chain utilizing it, utilizing waste product that we need to treat. $11 billion from our BIL, bipartisan infrastructure law, is going for cleaning up our acid mine drainage. Cleaning up in the sense it's only Band-Aid. putting sodium hydroxide. That's what we're paying for. After $11 billion, we'll ask for another $11 billion, or 12, 13, inflation. So this goes on now. If we can generate our own stuff, at least for defense industry. Because you guys know, every F-35 uses 1 ton of this material. And now, who is supplying? We know. And if we go against them, our tail will be cut. So that's the beauty of this process. So from lab scale, we can go to actually almost commercialization if we have our right industrial partners. So that's what it is. With China controlling most of these things, our nation needs it. That's for national security, industrial independence, and our researchers here at Penn State have developed this innovative solution here, and we have taken it from lab scale all the way to 10,000 gallons per day level to show, to demonstrate, and to get data also. It is not just to show off. You know, byproducts are there. What do we have to dispose? What kind of permits do we need? What kind of waste are we producing in this process? How much are we producing? What do we need to do to take care of these things? How much it costs? If we're doing it at a milligram level in a laboratory, it is different from actually doing it, and we have significant quantities and significant, actually more reliable, robust numbers to plug in and get the economic analysis done. As I said, economic analysis is a different ballgame. Whether it is economical or not, we need this for our country. So we are establishing this pilot scale facility. You have seen it virtually now. Any one of you, if you want to see our facility, it's our facility, folks. You can come, and our 24/7, as I always say to several people, 24/7 our doors are open, and you can come and see, and we will be happy. Our scholars will be happy to explain to you what we do out there. And if there is any way you guys can contribute to this, hey, Dumbo, you're not thinking about this, I can help you here, you're welcome. You're welcome. Okay, thank you very much. I hope we have enough time here for a question or two. All right.
Great, thank you.
Thank you very much. Thank you. Thank you for your patience.
I'm actually going to ask the first question from some people on Zoom are in the chat. Our first question is from David Russ.
Okay.
Is the state of PA providing or contemplating financial incentives for companies to construct/operate full-scale extraction plants?
Okay. I cannot talk for the government, but definitely state is considering. State is considering, and state is interested to support. And we are working with the state on how to do it. So I cannot tell you anymore. They did not write a check yet. But or even if they write a check, these days we cannot trust it until the bank says yes. Actually, even then we cannot say because it can be pulled back. So, but yes, to answer your question, David, yes, state is working. Actually, state has helped us in upgrading our facilities, actually, to be honest, analytical facilities and so on. So yes, I'm very grateful for that.
All right, any questions in the room here?
What is the concentration of solutes in this water, this AMD that you're running through this? Is it typical of lots of mine drainage, or is it a super duper one, or a low one, or?
Good question. Very good question. It is not, I mean, we cannot put a number to any particular site because it depends on the site. There are some sites that are rocket fuels. There are some sites that are acidic, but nothing related to our critical minerals or rare earth elements. There are a lot of silica dissolves, and a lot of things dissolve when they come in, but we don't have anything rare earth elements. There are some sites in southwestern Pennsylvania that we have tested. They are 4 times, 5 times better than what we are using as benchmark. We get it from Phillipsburg area, So it varies quite a bit. And the composition also varies depending on the coal mines water is going through, whether that original material had anything, depending on that. So yes, to give you an idea, actually, if we have 1.5 ppm of total rare earth elements in water, we're able to do it. We go from half to actually we have gone to about almost 2.5, 3 ppm of rare earth elements in the water. So that is the concentration that we're talking about here. I mean, these sludges, they have thousands of ppm, but they're all mixed back. So what we have to do processing is we need little more innovation. Like you people have to join the team now, looks like, because we need a little more innovation there, because it's at pH 7. It doesn't dissolve if you add water, so it has to go back down to 6.2 or whatever it is, and it needs more acid and things like that. It's like showing your nose like this. It's a roundabout way of doing it. I don't think it'll be economical. I can openly say that. Yes, please.
Yeah, going off that question, have you done research, or do you have an inclination into what is controlling the variation, if that is actual geologic variation in the coal beds themselves, or a lot of these coal mines were artisanal, and they were done over a huge amount of time when there were a huge amount of different processes employed? Is the rare earth element concentration primarily based on geologic initial composition or on processing method? And do you have an inkling?
Processing, they did not do any processing there, but geological things, I'm a zero when it comes to geological sciences. You guys know more than I do, definitely every one of you. Yes, Tim White and Maureen, they have been working with us to some extent on this one and characterizing some of these things. They have been very valuable players, but any one of you, if you can come on board, that would be good. To answer your question, simple. Yes, you got me. Yes.
Okay, I have one more on Zoom we can go.
All right.
to. This is from Paul Grabowski.
Yeah, Paul McCloskey.
Yes, he
Yeah.
sent this around 4:47 during your presentation, so it might be specific to a slide. But what is the durability of the equipment? How long does it last? How often does it need to be replaced, cleaned, refurbished?
Okay. The equipment that we are using is just to demonstrate. It is not, we did not design or we did not select the equipment based on for 30-year operation or 40-year operation. And also, we have some ideas, Paul. We want to simplify the process. First of all, we don't, in the field, if we put this plant up, we don't have to transport, and we don't need storage, the tanks, and we want to do it in a much simpler way. And definitely, it is not a 2-minute thing that I can explain you, but you and I, when we meet next time, I can explain you. We want to cut down the CapEx as much as possible to make it simple and rudimentary, like what they do with active treatment plants. That's what we want to do as much as possible. You know, if we have compressors, if we have control systems, if we have a lot of these things, then you need personnel, you need sophisticated methods to control. We want to minimize these things. So again, do I have a plan at this point? No. First, we want to check everything, and then that's the next step when it comes to engineering part. Thank you, Paul, for joining. Yes.
All right, we have time for one more in the room. Anybody else have a question? No?
No questions?
I have one more on Zoom I can ask.
Okay, you can
Okay.
go ahead, please.
This is from John Memmy. Sorry if
John Memmy, yeah.
Yes.
Hey, John, how are you?
He's asking, does magnetic separation technology have a role to play in the extraction process?
Yes, we are in the infancy stages to test that, actually, and I don't want to talk about our real research that we are doing until we are confident about it, but it may, depending on the form in which we precipitate some of these things, or even sludges. If we can use it, there is a chance. That's what I can say. We need to explore that, and what kind of Tesla or what kind of magnetic power we need to apply to get these things out. Those are the details that we still need to check out. Actually, yes.
Have you worked through some estimates of what you think the potential long-term production capacity is using this approach with acid mine drainage resources that we have in Pennsylvania? What can we get out of this?
We didn't do it, but there are estimates done by other people, and we can. And the goal of the United States Department of Energy is to get from these secondary sources 30 to 40% of our requirement at the end, not just acid mine drainage, but all secondary resources. That's the U.S. Goal.
How much? Yeah, all sorts of things like that.
Which means there are some estimates, and some schools and some folks, some data is actually generated by companies, and they don't want to reveal everything. But yes, there are estimates, and it is not a drop in a bucket. Maybe a drop in a bucket, but not a drop in an ocean. Let me put it that way. Yes, there is significant. Yes. You got another question?
What is the economics of what you're doing? I mean, you get enough rare earths and critical metals out at the end so that you can pay for it somehow? Where are you in figuring out what the economics might be?
I mean, as I mentioned, economics is something, in my opinion, our country's security is number one. So, but again, economic analysis is important for anyone. We will be in a better shape to get the more robust, reliable economics once we operate the plant, the pilot plant. Some of the economics that we have done, studies that we have done on a bench scale or even on the lab scale, they do not reflect the actual either energy consumptions or chemical consumptions or anything like that, the times. So that is one thing that we need to keep in mind, yes. But preliminary things show, I mean, this is the question, basic question. If we can cut down $11 billion of negative $11 billion that the taxpayer is spending or whatever out of pocket to minus $5 or $5 billion, is that a profit or is that not a profit? I don't know. I'm not an economist, but I think it would benefit taxpayer to some extent. And even the current people who by law have to treat it, they're spending through their nose to treat that water before they discharge, because right now regulations are very tight. It's not like abandoned coal mines, water comes out. It's not, great grandfather's property. So they are spending a ton of money. And if what they need to spend, let's say instead of $1,000, if they have to spend only $500, they're jumping up and down because that reduces their cost. But detailed economic studies, again, I can't comment on it yet at this point.
All right, that's about all we have time for today. Let's thank Sarma one more time.
Thank you. Thank you. It's always a pleasure to talk to my own colleagues here. It's a great, thank you very much for taking the time. And as I said, our plant is always open for you guys to come and see. Thank you.